Yes, I would also like to join in thanking the organizers, Manoj and Professor Sastry, for the amazing job they did in organizing this event. And yes, I'm very grateful to have had the chance to be here. Yes, my topic will be, yes, what is written there. Yes, so group will mean a finite group, and then we take the set of irreducible complex characters and the set of their degrees. So we don't care about, we forget about multiplicities. We are not giving the complex group algebra, but just the set of the degrees, different degrees. So the dimensions of irreducible complex representation. And the questions that we are going to address are the following. What kind of information can we read out this set of numbers? Is it okay, the microphone? Is it loud? Maybe second, what are the possible sets that can appear as character degrees of a group G? Yes, I'll survey some results, some classical results about this topic. One of the first, let's say, besides Ito's theorem, is the following. So now we are just concerned about the number of different character degrees. So one is always there. Of course, all the character degrees are one, then the group is abelian and conversely. If we have two character degrees, then Isaacs and Passman is 68. They classified this kind of groups. And you have two possibilities. So depending on M and on the fact that M is a prime power of naught. So if M is no prime power, or if it is a prime power, and the CEEL of the subgroups of the group are abelian, then you have this structure. Mod the center, you have a Frobenius group with a abelian kernel and complement, and the size of the complement, mod the center of the Frobenius complement, with respect to a central factor group. This is the only non-trivial irreducible character degree. If M is a prime power, power P, and the zero P subgroups are non-abelian, then you have two cases. Either you have just a prime P, according as a degree, and G as a normal abelian subgroup of index P, or the group is essentially a group of order P, so it's in fact it's a direct product of an abelian group and a group of in the zero P subgroup P. This doesn't change, so that this kind of products, of course, don't change the set of character degrees, all the multiplicities. So, in particular, when we have two character degrees, the group is solvable, and it has derived length 2. Also, they prove, Isaacs and Passman, that if you have 3 character degrees, then the group is still solvable, and the derived length is at most 3. This was way before the classification of finite simple groups, so they did it better. Yeah, this line of thought, one can say, okay, given a solvable group, is it possible to bound? And the answer is yes. The derived length of G in terms of the number of different character degrees, size of CB of G. Yes, already in the 30s, Taketa proved that if the group is monomial, which means every reducible character is induced by a linear character of some subgroup of the group, then the group is solvable and this bound holds. Then Berger proved that if we have an odd order group, then the same is true. Black proved that if you have a solvable group, then twice the size of the set of character degrees bounds the derived length of G. So it's still open whether, so one can omit in general the vector 2, which would give so the general bound, that bound there. But what has been proved more recently is that for solvable group, one has kind of logarithmic bound for the derived length of the vector group of G mod the fitting subgroup. This bound here. Another type of question is when these degrees have a particular, let's say, arithmetical structure. Some particular arithmetical structure, which is, in this case, well, are all primes. Can I speak without microphone? Good. If we assume that all the degrees are prime numbers, then what happens is that you can't have more than 2, and still a group is solvable. And yes, also the Isaacs and Passman, they characterize the structure of the group G. Yeah. Then prime powers were considered by Mans in 1995. So assume you see only prime powers, then you have these possibilities. Then if the group is solvable, then you can bound the derived length of G. Well, in fact, if you see 2 prime powers, the derived length of G is between 3 and 5. You see only 1 for the other 2. And if it is non-solvable, well, it's a complete characterization. Non-solvable groups are characterized. They are abelian times the product PSL24 or PSL28. In fact, those are the degrees also of those products. Yeah, that kind of results, as I mentioned already, can be seen like, yes, imposing some restriction. So what primes, how they appear, so what products of prime appear there can tell something about the structure of the group. In this sense, this is a, of course, very important result, which has been proved by Ito in the solvable or P-solvable, P is a relevant prime, the 50s, and then by Miller after the classification of multiple groups. If prime P does not divide the degree of any irreducible character of the group G, then the group has a normal abelian CLOP subgroup and convex. And also kind of dual of this is that if you see P in every degree, not 1, so abelian character degrees are multiple P, then G has a normal P complement. So this is an indication in this sense. And in order to explore this kind of connections, one could introduce some sort of combinatorial, let's say, object, a graph. There are several types of graph one could consider. This is one, and one takes, in general, take a set of finite numbers, a set of finite natural numbers. Take the prime divisors of those numbers. Those are the vertices of our graph delta, set X. And you join 2 primes. If it happens that the product of those 2 primes appears as a divisor of some of the member of this set. And as sets, which has been considered in the literature, the set of the order of the elements of G or in group order. And this, also the first one gives a so-called Bloomberg-Kegel graph, which has been studied. And and also, as is our case, the set of character degrees, or the set of class sizes. This is also considered. And what question can we ask? Of course, we cannot read out of a graph the isomorphic class of the group. We can read it even not from the character table. But we can ask whether there are some, so how this graph is influenced by the structure of the group, and what kind of graphs can appear as character degrees. Graphs, so graphs related to the second set. Well, I take the opportunity to mention this kind of connection between the graph bit on the set of character degrees and the one with the set of conjugates in class size. And it turns out, yeah, that one is always a subgraph of the other, which means, yes, which means that whenever you see two primes, which are divisors of some character degree together, their product divides, then the product divides also some size of some conjugacy class. It is not an induced subgraph. I mean, take a street. It is, so in the case of the street, the right graph is complete, and the other one is just two disjoint vertices. But it's a subgraph in general. So fine. Yes. What are we going to? Oh, I forgot to start there. Anyway, but I have the. Yeah, we write delta of G instead of delta of CD of G. We call it the character degree graph or the degree graph. Here is an example again, M11. Those are the character degrees. Primes appearing are 2, 3, 5, and 11. So the 10 means that 2 and the 5 are connected, and so on. 44, 11, 45, 3 and 5, and 55, 5 and 11. Oh, by the way, the character graphs of simple groups are known. Well, yes, here I would like to mention again Isomiller's theorem. It says in this setting that what are the vertices of this graph? Those are exactly the primes such that the CLOP subgroups are not contained in the fitting subgroup of G, and they are abelian. Yes, so we know what are the primes. And the edges, well, edges in general, they are not, of course, known so straight away. But there is this theorem which is to defend the tree. If the group is solvable and you have a missing edge, let's say between the primes vertices P and Q, then you have a bound on the P length and the Q length G by 2, and also the groups where both of them are 2 are characterized. So P length, well, just mention P length is the smallest number of P pieces you can see in a normal series in G. So about this graph, we can ask several questions. So classically, how many connected components can be there? The answer is not too many. They can be at most 3. There can be at most 3 connected components for general groups, finite groups. But in the solvable case, at most 2. And during those past years, groups with disconnected character graph have been classified. They have been classified by, well, a series of papers that Lewis gave the final classification for G solvable, and they fall in kind of 6, 7 families. And also for any G by Lewis and White. And yeah, in a sense, the classification for non-solvable groups is kind of clearer because there you have only, well, if the group has 3 connected components, then it is a direct product of an abelian group and a PSL2 to do the something. So PSL2 in characteristic 2. Or if it has 2 connected components, maybe then, for classification, it's not, I don't remember exactly, but anyway, if they are all 2 complete components, or one of them is not complete, and then the group has only one chief factor, which is non-abelian, and it is, again, a PSL2Q for some prime power Q. What about the diameter? So the size of the longest path inside the graph, well, it is at most 3. So the 2 results together can also, this one means that there are quite a few edges, so it doesn't happen that the group has many vertices, a small number of edges, so it's not always complete, but it goes in that direction in a sense. So the diameter is at most 3. There are groups of diameter 3. This is the degree graph of the Bianco group J1. It was, for some years, let's say 10, 15 years, there's been open the question of whether for solvable groups the diameter could be 2. There are good examples of diameter 2, but no example of G solvable with diameter, degree graph for diameter 3 were known for some years. But before saying that, maybe yes, I will now go through properties of the degree graph for solvable groups. So now I concentrate on solvable groups. So what are the results? This one is a very important result. So very nice in sense. It says that whenever you take 3 vertices inside this graph for a solvable group, then at least 2 of them have an edge. So I can add this. Or if we want to put it in the graph theory language, that the dependence number, so the size of the largest dependent set, which means no 2 vertices are adjacent set, is 2 in the delta of G for G solvable. And this, so to show that it's a very nice result, one can derive at once from this result, one can derive the following 2, because you cannot have more than 2 connected components because of this result. And also if you take, you have 2 connected components, take 2 vertices here, take 1 vertex here, of course these 2 ones cannot be adjacent, so the 2 ones here have to be adjacent. So it means that whenever the graph is connected, the connected components are complete. And also the diameter is at most 3, because this is also easy, because if you have a path of length 4, then you see that this result must have some extra edge. Another result that Dolfi proved in 2001 is the following. When you have 2 connected components for delta G solvable, one is very small. Let's say one is much bigger than the other. So if you, one is size n1, one the other n2, and then one is bigger, then you have that n1 is exponential. Yes, now, so I come back to this question about the diameter of this degree graph for G solvable. So it was conjecture that it was 2. Some people also said, maybe when I was doing my PhD with Minds, claimed so there were some rumors that it has been proved that the diameter was 2, but in fact no proof appeared because in fact it's not true. And we have an example. In Lewis 2002, he produced this example. We'll see in a minute how more or less it looks like. It has diameter 3 because 7 and 5, they are distance 3. So how is this group? So the order of this group is about 2 to the 60. So it's relatively large. And how is it done? So we have a normal CO2 subgroup over the 2 to the 45. It's made of 3 layers, which are the layers of the, so given by the terms of the lower central series. Each one of them is ordered to the 15, and on them, this cyclic group here is acting, and also this one is acting order 15. Let's say, like on each term, on the first 2 terms, I should say, so P of gamma 2, for instance, as a group of semilinear maps. Yeah. So it's acting on like this group here as a multiplicative group of the field of order 2 to the 15 on the field, and this is the Galois, say the Galois group. The action on here and here are the same, well, of this type, while the action of this last factor is kind of different because the subgroup here of order 7 is centralized elements here. And thinking that the group here of order 7 is the, so corresponds to the multiplicative group of the fixed field of the outcome of order 5 inside the Galois group, maybe gives so can maybe tell in some sense how 7 and 5 are actually the vertices at distance 3. So let's see how more or less the character degree graphs of the sections of these grouped up sections look like. We have, of course, E over P has an abelian, big abelian formal subgroup, so it will be degree 15 and 5. Then next section G, so P, so we mod out the commutator subgroup of P, we have this graph. Then mod out gamma 3 of G, still we have a disconnected graph of this type. Now the 2 appears, which was not there when, of course, we mod out the when we mod out the commutator subgroup of P, we have a normal abelian subgroup, 2 zero subgroup, so 2 is not the graph. But mod gamma 3 of P, yes, it's there, but still the graph is disconnected. And this is, okay, over gamma 4 we have G. Those are the degrees. And one can see that, yes, there is, so here is 11 degree connecting all together. Let's say here we are considering just in the graph, we're just considering 2 by 2, but we could also consider some sort of Fisheye complex, let's say, considering so higher dimension when dimension 3 when 3 primes can come together and so on. But still, okay, here we are concerned about 2 at the time. Anyway, you can see that yes, the 2 here 2 7 anyway, we get this graph here. So an example. There are some questions. So it's quite big example. So Lewis he asked, is it example minimal? Can we have smaller ones? What can we say about the structure of solvable groups of diameter 3? So graph of diameter 3. For example, the fitting height, which means there's smallest number of nilpotent layers in a series. And also, this is it true, as it happens in that example, that we have a normal subgroup, in that case, the gamma 3 of P, such that the vertices are the same. So vertices of delta G over N are the same vertices of delta over G, so we lose no vertex, but the graph for G over N is disconnected. Does it happen? Yeah, this example. Yes. And also, final question. Can the set of vertices of G can be partitioned into subsets, one much bigger than the other, as it happens in this case? Well, this will, if the first question has an answer yes, then the second will follow easily. Yeah. So this is the joint work with Carlo Fasolo, Manuel Pacific, Lucia Sanus, but also a former PhD student of Lewis, Catherine Sass, has obtained more or less the same results. So they are overlapping, but not quite. Those results are not quite the same. So that are independent papers. And yes, what are the answers? There exists, if we have a solvable group, diameter 3, there exists only one prime P on one and only one, such that G has a normal on a million, 0P subgroup, then P complement. And the structure of the fitting of the group is more or less this. Okay, yes. Yeah, we have the fitting is P times the centralizer in H of P, but the centralizer H of P is central in G. And the structure of H is known. It is, I put somewhere definition of linear groups, just not here. It's a semilinear group again, so we have that it has, it's not important, it has cyclic silos, all cyclic. So it's a metacyclic group, and yes, those, yeah, that implies that the fitting I of G is 3. Yes, also we could give some kind of more detailed structure of the actions. So if I have the definition, yes, this is the, yeah, just the definition of this semilinear group. It's a set of those maps, multiplication by non-zero element of the field, where K is a field over the N, and sequence a Galois group of K over the prime field. Then inside the normal zero abelian zero group P, we have this series. We take, well, first we take the commutator of GP. We suspect, we think that it splits on this extension splits, but we are not sure. So anyway, we take this, and then from here downwards, we have a series of modules, all of the same dimension, which are all embeddable as irreducible subgroups in this. So I mean, G over a centralizer in G of each of those sections, order, all of the same order P to the N, all of those groups embed to gamma P to the N. Yes, this also gives us that in general we have this kind of situation. Those are the graphs. Take the phi1 is a set of prime divisors of the fitting of H, which we call X, of, yes, over A, and pi2 is the Galois. We have this kind of behavior, general behavior, when we go down the spectrum groups. So this is, yes, I think, sorry. I think I should stress this is so what took us most of the work to prove that still, when we factor out gamma 3 of P, the graph is still disconnected. Okay, and then, well, this is a concept. What we see here, so this bigger column part, which is this one, here, the graph the other comes essentially from the fact that this group here gives a disconnected graph. And then we can apply Palfi's result. So it's something that we can read already at this level. But so this level gives us some more information, let's say. Yes. Okay, now we can also say that this example is as small as possible. Yes, because maybe I forgot to mention here that n, which is the index of x and h, is divisible by at least 2 odd primes. We can prove this because of the semilinear nature and some Clifford theorem. Then, when we get to the odd, we can also prove that called D, the index of each group of H, we have that this x over A is order divisible by this number, and then one easily gets that. So the order of G is at least this. So since n is divisible by 2 odd factors, so n is at least different primes, n is at least 15. So here, SAS approach was a bit more on the graph side, and yes, she proved that the over gamma 2 of B, the graph is disconnected, but not over gamma 3. What she proved is that also that she was classifying what kind of graphs one can have as degree graphs with 6 vertices and diameter 3. So what we have here, this is Lewis graph. So she proved that we cannot have any graph where we delay one. This is has diameter 3 and respects the Palfi condition, so every 3 vertices have at least one edge, but cannot come out as a characteristic degree graph of a solvable group. This one and also this one. So those are not there. Yes, now I'd like to switch quickly to another. We have 14 minutes, so should stop 10 minutes. Yeah. So yes, consider a graph. The complement graph is a graph on the same set of vertices with complementary set of edges. So you put an edge when it was not there in the graph. So why are we interested? Okay, there is an example. You take the C5, and this is a self-complementary graph. C5 is great. How can we rephrase Palfi's theorem? It says that for a solvable group, the complementary degree graph does not contain any cycle of length 3. Yes, so by some other problem, we got to consider the problem. Okay, what about cycles of odd length? Because you see, when you have a disconnected graph, then the complementary graph is a complete bipartite graph. So we certainly have, when we have more than one vertex components, we have cycles of length 4. But so length 5 is impossible, any odd length. And so I, in a sense, surprisingly, we could prove that this is not the case. So a complementary graph does not contain any cycle of odd length, which means it's a bipartite graph. And so we can have some consequence of this that bipartite means that in the complementary graph, there are the components. Those are independent sets, which means that if you see that in the normal graph, in the positive graph, you see that those are induced complete subgraphs. So we have a partition of the vertex set of graph with 2 two sets that use complete subgraphs. Okay, so in particular, you have a subset of vertices which induce a complete subgraph. It has at most half of the vertices. So this is another way of saying that. And this is, I'd like to mention a kind of some, well, not very strong, maybe kind of evidence towards what's called Hooper's proxy conjecture, which is like this. Conjecture means that in the case of solvable groups, you have a character whose degree is divisible by at least half of the primes that divide the degree of any character. In the case of general group, it's 3, of course. For instance, take A5 has just prime power. Yes. And, well, of course, here when we consider the graph delta, we are taking 2 primes at a time. So we are building up a complete graph by so it's kind. Anyway, it's and yeah, maybe one last application of this complementary graph is the following. Yeah. If you consider a set of 3 vertices, 3 vertices Dolfi for a solvable group in a degree graph, you have an edge. Now with this result, so maybe just saying that you have no C5 inside the complement graph, you can say that whatever set of 5 vertices, taking delta of G is solvable, then there is a complete triangle between them. And this is, because if you, the only way of having a 2 coloring of a complete graph on 5 vertices is the following. That you take. Sorry, I would say of the edges. So yeah, if we take the complete graph on 6 vertices and any 2 coloring as a monochromatic triangle, this is very fast result comes here. The only coloring for the A5 is, with 2 colors is this, which doesn't contain triangles. So now if we think at colors like an edge being in the delta or other color, the edge being in the delta bar, the complementary graph. Yeah, since we cannot have triangles by Dolfi's theorem delta bar, and we cannot have C5 delta bar of delta, we have that this is not possible. So every 5 vertices, so there are every 5 vertices there is a subset of 3 vertices that give you a C3 delta G. Yeah, I was thinking about some idea of proofs, but